combined radiation from these disks can make the centres of galaxies shine with incredible brightness. Some of the brightest objects in the universe are powered by supermassive black holes consuming surrounding material. These objects are known as quasars. Quasars appear as brilliant points of light visible across billions of light-years of space. Despite their small appearance in telescopes, they release enormous amounts of energy. In fact, a single quasar can outshine the combined light of all the stars in the galaxy that contains it. The heat generated within the accretion disk of a quasar reaches extraordinary levels. Gas spiralling into the central black hole becomes so energetic that it produces intense radiation across the electromagnetic spectrum. The disk glows with extreme brightness as matter races inward at tremendous speeds. In addition to the disk itself, some black hole systems produce enormous jets of energy. Magnetic fields within the accretion disk can channel some of the surrounding plasma into narrow beams that shoot outward along the black hole's rotational axis. These jets travel vast distances into space, sometimes extending far beyond the boundaries of the host galaxy. Particles inside these jets move close to the speed of light. Although the jets themselves are not necessarily the hottest regions near the black hole, they represent another example of how energy released by accretion disks can influence enormous regions of space. Astronomers continue studying accretion disks to understand how matter behaves under such extreme conditions. The physics involved include strong gravity, high temperatures, intense magnetic fields, and relativistic effects predicted by Einstein's theory of general relativity. All of these factors combine to create environments unlike anything found elsewhere in the universe. Yet even though accretion disks are extraordinarily hot, they're still not the hottest conditions that have ever existed. Not long after astronomers began studying the universe with radio telescopes in the 20th century, they noticed something puzzling. Some objects in the sky appeared almost like ordinary stars through optical telescopes, just tiny points of light. Yet when scientists examined their radio signals and spectra, those points behaved nothing like normal stars. The radiation coming from them was far too powerful. These objects were eventually given the name quasars, short for quasi-stellar radio sources. The name reflects the way they first appeared, star-like in telescopes, but clearly something much more energetic. As astronomers studied quasars more carefully, the scale of what they were observing became clear. Quasars are not stars at all. They are the incredibly bright centres of distant galaxies, powered by supermassive black holes consuming enormous amounts of matter. The heat and radiation produced in those regions make quasars some of the most luminous objects ever observed. To understand why quasars become so bright and hot, imagine what happens when vast clouds of gas fall toward a supermassive black hole. Earlier, we explored how accretion disks form when material spirals inward. In quasars, this process occurs on a much larger scale. The central black hole may contain millions or even billions of times the mass of the Sun. The surrounding disk of gas stretches across distances comparable to the entire solar system or larger. Gas drawn toward the black hole does not fall quietly. It collides, compresses, and accelerates as gravity pulls it closer to the centre. Friction between particles converts enormous amounts of gravitational energy into heat. The disk grows hotter and hotter as the material spirals inward. The temperatures reached in these regions are extraordinary. Outer portions of the disk may glow with temperatures of several thousand degrees, producing visible light similar to that emitted by stars. Moving closer toward the black hole, temperatures rise dramatically. Inner regions of the disk can reach tens of millions of degrees Celsius. At those temperatures, matter becomes an extremely energetic plasma that emits intense ultraviolet radiation and X-rays. The radiation pouring out of a quasar can be so powerful that it illuminates gas across the entire host galaxy. Even from billions of light-years away, quasars can appear brighter than many closer galaxies. When astronomers first realized how distant quasars were, the discovery was astonishing. Objects that appeared faint in telescopes turned out to be unimaginably far away. Their brightness implied that they were releasing more energy than entire galaxies filled with billions of stars. At first, scientists struggled to explain how anything could generate that much energy. The solution became clearer once astronomers understood the role of supermassive black holes. As matter falls into a black hole's accretion disk, the conversion of gravitational energy into radiation can be extremely efficient. In fact, This process can release more energy per kilogram of material than nuclear fusion inside stars. The energy comes from the gravitational potential of matter falling into a deep gravitational well. As particles spiral inward, they lose energy through friction and collisions. That energy escapes in the form of heat and radiation. A quasar can shine with the brightness of trillions of suns. Despite that enormous output, the actual region producing the radiation is relatively small compared with the size of the galaxy surrounding it. Most of the visible light comes from the accretion disk itself, where temperatures are highest. Astronomers studying quasars often examine their spectra, the spread of light across different wavelengths. These spectra reveal information about the temperature and motion of gas near the black hole. Some spectral lines appear broadened or shifted because the gas in the disk is moving extremely fast. The inner regions of the disk may orbit the black hole at significant fractions of the speed of light. When gas moves that quickly, the light it emits is affected by relativistic effects predicted by Einstein's theory of relativity. Astronomers can analyze these changes to estimate how close the gas lies to the event horizon. Another fascinating feature of quasars involves the enormous jets that sometimes emerge from the central region. Magnetic fields surrounding the black hole and its accretion disk can channel some of the plasma into narrow beams that shoot outward along the rotational axis. These jets travel far beyond the central galaxy, sometimes extending for hundreds of thousands of light years. Particles within these jets move at speeds approaching the speed of light. Although the jets themselves are not necessarily the hottest regions, they carry enormous amounts of energy away from the central engine. As the particles travel outward, they interact with surrounding gas and magnetic fields, producing radio waves, X-rays, and sometimes gamma rays. Observing these jets helps astronomers understand how energy from the black hole influences the surrounding galaxy. Quasars also play an important role in the history of the universe. Many of the brightest quasars are observed at extremely large distances, meaning their light has been travelling toward Earth for billions of years. When astronomers observe those objects, they are seeing them as they existed in the early universe. During that time, galaxies were still forming and growing. Supermassive black holes in young galaxies often had abundant gas falling toward them. As a result, quasar activity was much more common in the early universe than it is today. Over time, many galaxies consumed or expelled much of the gas near their centres. Without that fuel, the accretion disks faded and the quasars grew quieter. Our own galaxy contains a supermassive black hole at its centre called Sagittarius A star. Compared with quasar engines, however, Sagittarius A star is relatively calm at the moment. Only small amounts of gas fall toward it, producing faint radiation compared with the brilliant output of active quasars. Yet astronomers suspect that the centre of the Milky Way may have been much more active in the distant past. Evidence suggests that bursts of energetic activity occurred long ago, possibly when larger amounts of gas were available near the central black hole. If our galaxy had experienced a full quasar phase, the centre of the Milky Way might once have shone far more brightly than it does today. Studying quasars also allows scientists to examine the material that lies between galaxies. As the intense light from a distant quasar travels across the universe, it passes through clouds of gas along the way. Each cloud absorbs specific wavelengths of light depending on its composition. When astronomers analyse the quasar's spectrum, they can see these absorption patterns and learn about the material that the light passed through on its journey. In this way, quasars act like powerful cosmic flashlights, illuminating the otherwise invisible gas scattered throughout intergalactic space. The extraordinary temperatures and energies present near quasars demonstrate just how extreme gravitational heating can become. Matter falling toward a supermassive black hole releases vast amounts of energy before crossing the event horizon. Despite the incredible heat of these environments, however, they still do not represent the most extreme temperatures that have existed in the universe. Long before stars ignited, before galaxies formed, and long before planets or oceans existed, the universe was a very different place. There were no shining suns, no drifting clouds of gas, and no quiet stretches of empty space between galaxies. In the earliest moments of cosmic history, everything that would one day become the vast universe we see today existed in a much smaller, denser, and unimaginably hotter state. If we could travel back far enough in time, the entire observable universe would appear as an intensely bright, compact region filled with energy. Temperatures were so extreme that the familiar building blocks of matter, Atoms, molecules, even atomic nuclei could not exist yet. Everything was immersed in a blazing ocean of particles and radiation. This period began with the event we call the Big Bang. The term Big Bang sometimes creates the impression of a conventional explosion, like a bomb detonating in empty space. But the reality is more subtle than that. The Big Bang was not an explosion within space. It was the expansion of space itself from an extremely dense and hot state. Every region of the universe expanded simultaneously. In those earliest moments, temperatures were extraordinarily high. Physicists estimate that immediately after the beginning, temperatures may have reached around 10 to the 32nd power Kelvin. That number is almost impossible to imagine. It is far beyond the temperatures found in stars, supernovae, or even the violent accretion disks around black holes. At such extreme temperatures, the known forces of nature behaved very differently from the way we experience them today. The familiar distinctions between particles and energy become less clear. Matter and radiation existed together in a kind of energetic mixture, where particles constantly collided, transformed, and reformed. But the earliest instant of the universe remains difficult to describe with certainty. Our current physical theories allow scientists to trace the evolution of the universe back to a fraction of a second after the beginning. Earlier than that, conditions become so extreme that the equations used in modern physics stop providing reliable answers. Researchers believe that understanding those earliest instants will require a future theory that successfully combines quantum mechanics with gravity. Even without knowing the details of the very first moment, scientists can still describe what happened soon afterward. Within the first tiny fraction of a second, the universe expanded rapidly and cooled slightly, though the temperatures remained unimaginably high. Energy dominated everything. Particles appeared and disappeared constantly through high-energy interactions. During this period, the universe was filled with fundamental particles such as quarks, gluons, electrons, neutrinos, and photons. These particles collided continuously in an environment so energetic that the usual structure of matter could not form. Quarks, which normally combine to create protons and neutrons, moved freely in a dense plasma. Gluons, the particles responsible for holding quarks together inside atomic nuclei, were also free in this energetic mixture. Physicists refer to this state as quark-gluon plasma. In this early phase, temperatures exceeded trillions of degrees. Under such conditions, particles possessed enormous kinetic energy, moving and colliding at tremendous speeds. Matter existed in a form very different from anything encountered in everyday life. As the universe continued expanding, it gradually cooled. After about 1/1,000,000th of a second, the temperature had dropped enough for quarks to begin binding together. They combined to form protons and neutrons, the particles that make up the nuclei of atoms. This transition marked an important milestone in cosmic history. For the first time, stable structures began forming within the expanding universe. The temperature at that stage was still around 1,000,000,000 degrees Celsius. That number may seem astonishing, but it represented a dramatic cooling compared with the earlier moments. In the rapidly expanding universe, temperature dropped as space itself grew larger. Energy spread out over an increasing volume, allowing particles to settle into more stable arrangements. Over the next few minutes, another key process took place. Protons and neutrons began combining to form the nuclei of the lightest elements. This process is known as Big Bang nucleosynthesis. During these first minutes, the universe produced the nuclei of hydrogen, helium, and small amounts of lithium. These elements would later become the building blocks of stars and galaxies. Temperatures during this stage remained extremely high, roughly billions of degrees. Nuclear reactions occurred constantly as particles collided within the dense plasma filling the universe. Eventually, as expansion continued, the universe cooled enough that nuclear reactions slowed down and stopped. The early mixture of hydrogen and helium remained as the primary composition of matter throughout the cosmos. At this point, however, the universe was still far too hot for atoms to form. Electrons moved freely through space, constantly scattering off photons and atomic nuclei. Light could not travel very far without colliding with charged particles. The entire universe behaved like a glowing fog of plasma. This situation lasted for hundreds of thousands of years. During that time, the universe continued expanding and cooling gradually. Temperatures slowly dropped from billions of degrees to thousands of degrees. Although this was a dramatic change compared with the early moments, it still meant the cosmos remained hotter than most stellar surfaces. Eventually, the temperature fell to around 3000 degrees Celsius. At this point, conditions allowed electrons to combine with atomic nuclei and form neutral atoms for the first time. Hydrogen atoms appeared throughout the universe, along with helium atoms created earlier during nuclear synthesis. Once electrons became bound within atoms, photons could travel freely without constantly scattering. Light that had been trapped inside the cosmic plasma suddenly began moving through space unobstructed. This event is known as recombination. The radiation released at that moment still exists today. As the universe continued expanding, the wavelength of that ancient light stretched and cooled. Today we observe it as the cosmic microwave background, a faint glow filling all of space. That radiation represents the oldest light we can currently detect. Measurements of the cosmic microwave background provide scientists with detailed information about the early universe. Tiny variations in temperature within this radiation reveal how matter was distributed shortly after recombination. Over billions of years, those small fluctuations grew under the influence of gravity. Regions containing slightly more matter pulled in surrounding gas, eventually forming the first stars and galaxies. Looking back at the earliest phases of the universe reveals something remarkable. The hottest place that has ever existed was not a star, a black hole, or a supernova. It was the universe itself during its earliest moments. Every region of space shared those extreme temperatures. Instead of isolated hotspots, the entire cosmos existed as a uniform ocean of energy and particles at unimaginable heat. As expansion continued, that energy spread outward, cooling the universe and allowing structure to form. Stars ignited, galaxies assembled, planets, and eventually life appeared within certain regions. Yet the extreme temperatures of the early universe did not disappear entirely from scientific study. Although we cannot travel back to those moments directly, physicists have found ways to recreate tiny pieces of that ancient environment here on Earth. It might seem surprising that some of the most extreme temperatures ever created did not occur in distant galaxies or violent stellar explosions, but inside enormous laboratories here on Earth. While the universe produced unimaginable heat during its earliest moments, scientists have found ways to briefly recreate similar conditions, using machines designed to accelerate particles to extraordinary speeds. These machines are known as particle accelerators. Particle accelerators are among the largest scientific instruments ever built. Their purpose is to take tiny particles, often protons or atomic nuclei, and push them to incredibly high velocities. By accelerating these particles and then allowing them to collide, scientists can release tremendous amounts of energy in a very small space. When those collisions occur, the energy concentrated in the impact zone can momentarily create temperatures far beyond those found in stars or supernova remnants. The most famous of these machines is the Large Hadron Collider, often called the LHC. The LHC is located near Geneva, Switzerland, in a circular tunnel about 27 kilometers in circumference. This enormous ring sits deep underground and contains powerful magnets that guide and accelerate beams of particles moving close to the speed of light. Inside the collider, beams of protons or heavier atomic nuclei travel in opposite directions around the ring. When the beams reach the desired energy, they are directed to cross paths at specific points where detectors are positioned. At those crossing points, the particles collide. These collisions occur at velocities extremely close to the speed of light. When two particles meet with such energy, their kinetic energy transforms into a burst of new particles and radiation. According to Einstein's equation, energy can convert directly into mass. The collision zone briefly contains a dense cloud of newly created particles moving in every direction. During these tiny instants, temperatures can reach extraordinary levels. In certain experiments involving collisions between heavy ions, such as lead nuclei, scientists have produced temperatures exceeding several trillion degrees Celsius. That is far hotter than the interior of any star, and hotter even than many supernova explosions. These extreme conditions last for only a fraction of a second, but they allow physicists to study how matter behaves when energy density becomes incredibly high. The reason scientists aim for such extreme temperatures is to recreate a particular state of matter that existed in the early universe. Earlier we discussed the quark-gluon plasma that filled the cosmos shortly after the Big Bang. Under ordinary conditions, quarks are confined within protons and neutrons. They cannot move freely because they are bound together by the strong nuclear force, but when temperatures rise above a certain threshold, that confinement breaks down. In the intense environment created by particle collisions, protons and neutrons can briefly melt into their fundamental components. Quarks and gluons move freely within a tiny region of space, forming a fluid-like state known as quark-gluon plasma. This state of matter behaves in fascinating ways. Rather than acting like a gas of independent particles, quark-gluon plasma flows more like a nearly perfect liquid. Experiments have shown that it has extremely low viscosity, meaning it moves with very little resistance. This discovery surprised many scientists because they initially expected the plasma to behave more like a thin gas. Studying quark-gluon plasma helps physicists understand how matter transitioned from its earliest form into the particles and atoms that make up the modern universe. In the first microseconds after the Big Bang, the entire universe was filled with this plasma. As the universe expanded and cooled, quarks combined into protons and neutrons, eventually leading to the formation of atomic nuclei. By recreating similar conditions in the laboratory, researchers can investigate how that transition occurred. The detectors surrounding particle collisions are among the most complex scientific instruments ever built. When particles collide inside an accelerator, they produce showers of new particles that spread outward in all directions. Detectors track the paths, energies, and identities of these particles. By analysing the resulting data, scientists reconstruct what happened during the collision. The amount of information collected in each experiment is enormous. Thousands of collisions may occur every second. Each collision generates large volumes of data describing the behaviour of dozens or even hundreds of particles. Powerful computers analyse these events, searching for patterns that reveal new insights about fundamental physics. The detectors themselves are built in layers, each designed to measure different aspects of the collision. Some layers track the paths of charged particles using sensitive electronic sensors. Others measure energy by absorbing particles and recording the resulting signals. Still others detect particles that rarely interact with matter, such as neutrinos. Together, these systems allow scientists to observe events occurring within regions smaller than an atomic nucleus. Despite the complexity of these machines, the basic idea remains straightforward. Concentrate energy into an extremely small space for an extremely short time. When that happens, temperatures rise dramatically. The temperature reached in heavy ion collisions at the LHC and similar accelerators has been estimated at around 5 trillion degrees Celsius. That number represents one of the highest temperatures ever measured in a controlled experiment. At such temperatures, ordinary matter cannot exist. Instead of atoms or even atomic nuclei, the collision region contains a dense mixture of quarks, gluons, and other fundamental particles moving with tremendous energy. Although these conditions exist for only a brief instant, they provide a valuable window into the physics of the early universe. Particle accelerators around the world contribute to this research. In addition to the LHC, facilities such as the Relativistic Heavy Ion Collider in the United States conduct experiments specifically designed to study quark-gluon plasma. Each experiment adds new data that helps scientists refine their understanding of high-energy matter. These experiments also reveal how energy transforms into new forms of matter. During collisions, particles not normally present in everyday environments can appear. Some exist only briefly before decaying into other particles. Observing these processes helps physicists test theoretical models describing the fundamental forces of nature. One of the most famous discoveries associated with particle accelerators occurred in 2012, when scientists confirmed the existence of the Higgs boson. The Higgs boson plays a crucial role in explaining why certain particles have mass. Its discovery provided strong support for the standard model of particle physics, the framework scientists use to describe the behaviour of fundamental particles. Although the Higgs boson itself is not directly related to extreme temperatures, its discovery highlights how particle accelerators allow scientists to explore conditions and phenomena impossible to observe under ordinary circumstances. What makes these experiments especially interesting in the context of temperature is the scale difference involved. The region where a particle collision occurs is unimaginably small. It is far smaller than a grain of sand, smaller even than an atom. Yet within that tiny space, temperatures surpass those found in most cosmic environments. The reason this is possible lies in energy density. By concentrating large amounts of energy into a microscopic volume, Scientists create conditions where particles move with incredible energy. Temperature, which measures the average kinetic energy of particles, rises accordingly. Even though the high temperature lasts only for a brief instant, it represents a genuine physical state that can be studied and measured. These laboratory experiments remind us that extreme heat is not limited to distant stars or galaxies. Under the right conditions, the fundamental laws of physics allow such temperatures to appear anywhere energy becomes sufficiently concentrated. Imagine matter heated so intensely that even the particles inside atomic nuclei begin to separate. Not atoms breaking apart, but the protons and neutrons themselves dissolving into their most fundamental ingredients. That is the state physicists call quark-gluon plasma, and it represents one of the hottest forms of matter ever produced. Under ordinary conditions, the structure of matter is surprisingly stable. Atoms consist of electrons orbiting a nucleus made of protons and neutrons. Those protons and neutrons are themselves built from smaller particles called quarks, which are held together by gluons. The strong nuclear force binds them so tightly that individual quarks are never observed on their own in everyday environments. Even inside stars where temperatures reach millions of degrees, protons and neutrons remain intact. Their internal structure stays locked together by that powerful force. But temperature measures the energy of moving particles, and if the energy becomes high enough, even the strong force can be temporarily overcome. When temperatures climb into the trillions of degrees, the boundaries between protons and neutrons begin to dissolve. The quarks inside them are no longer confined to individual particles. Instead, they move freely within a dense, energetic mixture, along with the gluons that normally hold them together. That mixture is quark-gluon plasma. In this state, matter behaves very differently from anything familiar in daily life. Instead of solid objects, liquids, or gases made of atoms, the material becomes a kind of particle fluid composed of the building blocks of nuclear matter. Understanding this unusual state helps scientists study the earliest moments of the universe. Shortly after the Big Bang, the universe was far too hot for protons and neutrons to exist as stable particles. The entire cosmos was filled with quark-gluon plasma. As the universe expanded and cooled, quarks gradually combined into protons and neutrons, allowing atomic nuclei and eventually atoms to form. For a long time, that ancient phase existed only in theory. Physicists predicted that such a state should appear at extremely high temperatures, but recreating those conditions seemed impossible. The temperatures required are far beyond those found in everyday environments, and even the cores of stars are not hot enough. Eventually, particle accelerators provided a way to approach those conditions. When heavy atomic nuclei are accelerated to nearly the speed of light and smashed together, enormous amounts of energy are concentrated in a tiny region of space. For a brief instant, the energy density becomes high enough to melt protons and neutrons into quark-gluon plasma. These collisions occur in facilities such as the relativistic Heavy Ion Collider in the United States and the Large Hadron Collider in Europe. Inside these machines, beams of heavy ions, often lead or gold nuclei, race through circular tunnels guided by powerful magnets. When two beams collide, the impact creates a microscopic fireball where temperatures can exceed several trillion degrees Celsius. The fireball expands and cools almost immediately, but during that tiny fraction of a second, quark-gluon plasma exists. Because the state disappears so quickly, scientists cannot observe it directly in the way one might examine a solid object. Instead, they study the particles produced as the plasma cools and transitions back into ordinary matter. Detectors surrounding the collision point record the paths, energies, and identities of thousands of particles emerging from each event. By analysing patterns in these particles, researchers reconstruct how the plasma behaved before it cooled. One of the most surprising discoveries about quark-gluon plasma is that it behaves more like a liquid than a gas. At first, physicists expected the freed quarks and gluons to move independently, forming a chaotic cloud of particles. Instead, experiments showed that the plasma flows smoothly, almost like a perfect fluid. In fact, quark-gluon plasma appears to have one of the lowest viscosities ever measured. Viscosity describes how easily a fluid flows. Water flows easily compared with honey, which has higher viscosity. Quark-gluon plasma flows even more freely than water. The particles inside it move collectively, responding to pressure gradients and forming patterns similar to fluid currents. This behaviour suggests that the strong force between quarks and gluons remains influential even in this high-energy state. Rather than moving entirely independently, the particles still interact strongly with one another, creating coordinated motion across the plasma. The discovery reshaped scientists' understanding of how fundamental particles behave under extreme conditions. Another fascinating aspect of quark-gluon plasma involves the enormous pressure within the collision zone. When two heavy nuclei collide at high energy, the resulting plasma expands rapidly outward. The pressure gradients created during the collision cause particles to move in characteristic patterns that detectors can measure. One such pattern is known as elliptic flow. Because the overlapping region between the colliding nuclei has an elongated shape, the plasma expands more easily in certain directions than others. This directional expansion leaves measurable signatures in the particles that emerge. Studying these patterns helps researchers determine properties such as the viscosity and temperature of the plasma. Although the plasma exists for only a tiny fraction of a second, its properties reveal important details about the physics of the early universe. The temperatures reached in these experiments are astonishing. The quark-gluon plasma created in heavy ion collisions can reach temperatures around 5 trillion degrees Celsius. To put that into perspective, the core of the Sun reaches about 15 million degrees. Even supernova explosions typically reach temperatures in the billions of degrees. The plasma produced in particle accelerators is hundreds of thousands of times hotter than the centre of our star. Despite these incredible temperatures, the region where the plasma forms is incredibly small. The fireball created in a heavy ion collision measures only a few femtometers across. A femtometer is 1 quadrillionth of a meter, roughly the size of an atomic nucleus. Within that tiny space, however, energy becomes so concentrated that matter enters one of the hottest states ever observed. Because the plasma cools almost instantly, it transitions back into ordinary particles such as protons, neutrons, and mesons. These particles fly outward from the collision point and are captured by detectors. By analysing their trajectories and energies, scientists reconstruct the evolution of the plasma during its brief existence. Each collision provides a tiny snapshot of high-energy physics. Researchers repeat the experiments millions of times, gathering enough data to reveal consistent patterns. Over years of study, these experiments have confirmed that quark-gluon plasma behaves as predicted in many theoretical models. The work continues as physicists refine their understanding of this remarkable state of matter. Exploring quark-gluon plasma not only teaches us about the early universe, but also helps improve theories describing the strong nuclear force. This force governs how quarks interact with each other and plays a central role in the structure of matter. Understanding it more fully could lead to deeper insights into the behaviour of fundamental particles. Although quark-gluon plasma represents one of the hottest forms of matter ever produced, it does not occur naturally in most places today. The universe cooled rapidly after the Big Bang, allowing protons and neutrons to form and remain stable. Only in rare environments, such as the cores of neutron star collisions or the tiny fireballs created in particle accelerators, do conditions briefly return to this primordial state. Still, the fact that humans can recreate such extreme temperatures in laboratory experiments reveals something remarkable about the power of modern science. With carefully designed machines and detectors, scientists can study matter under conditions similar to those that existed when the universe was less than a microsecond old. Sometimes the hottest conditions in the universe are not found in a place you can point to, like the surface of a star or the swirling gas around a black hole. Instead, they exist inside individual particles racing through space with extraordinary energy. These particles are known as cosmic rays. Despite the name, cosmic rays are not rays in the usual sense. Most of them are individual atomic nuclei, often just single protons, that travel across the universe at speeds extremely close to the speed of light. They originate from some of the most energetic events known in astrophysics, and carry enormous amounts of energy packed into a single particle. Cosmic rays are constantly arriving at Earth. Every second, particles from deep space strike our atmosphere. Most pass unnoticed, colliding with atoms high above the surface and producing cascades of secondary particles. These particle showers spread through the atmosphere before disappearing long before they reach the ground. The majority of cosmic rays have relatively modest energies compared with the most extreme examples. Many are produced by ordinary astrophysical processes such as supernova explosions or strong magnetic activity around stars. But a small fraction of cosmic rays possess energies so enormous that they challenge our understanding of how the universe accelerates particles. These are known as ultra-high energy cosmic rays. Some of these particles carry as much kinetic energy as a well-thrown baseball, yet all of that energy is concentrated within a single atomic nucleus. The comparison may sound unusual, but it illustrates just how energetic these particles can be. Imagine shrinking the energy of a thrown ball down to something far smaller than an atom. That is roughly the scale involved. To reach such energies, cosmic rays must be accelerated by some of the most powerful environments in the universe. One likely source involves supernova remnants. When a massive star explodes, the expanding shockwave moves outward through surrounding gas at tremendous speed. Charged particles caught in these shockwaves can bounce back and forth across the shock front, gaining energy with each pass. Over time, this process can accelerate particles to very high speeds. Another possible source involves the powerful magnetic fields near neutron stars or black holes. In those regions, intense gravitational and magnetic forces can fling charged particles outward with enormous energy. Active galaxies containing quasars may also accelerate particles to extreme speeds through interactions with their enormous jets of plasma. Once accelerated, cosmic rays begin long journeys through interstellar and intergalactic space. Unlike photons, which travel in straight lines, charged particles are affected by magnetic fields. The universe is threaded with weak magnetic fields associated with stars, galaxies, and clusters of galaxies. As cosmic rays travel, these magnetic fields deflect their paths. The result is that by the time a cosmic ray reaches Earth, it may have taken a complex and winding route through space. This makes it difficult to determine exactly where a particular particle originated. Still, by studying large numbers of cosmic rays and analysing their energies, scientists can learn about the environments that produced them. When cosmic rays reach Earth, they encounter the atmosphere. A high-energy cosmic ray colliding with an atmospheric atom produces a chain reaction. The collision generates secondary particles such as pions, muons, and electrons. These particles in turn collide with other atoms, creating a shower that spreads outward as it travels downward. Large detectors on the ground can observe these showers. Some observatories cover vast areas in order to capture the rarest and most energetic events. One of the largest is the Pierre Auger Observatory in Argentina, which spreads across thousands of square kilometres of open land. The observatory uses hundreds of detectors placed across the landscape to measure the arrival of particle showers. When a cosmic ray strikes the atmosphere and creates a cascade of particles, the detectors record the signals produced as those particles pass through. By analysing the pattern of signals across many detectors, scientists can reconstruct the direction and energy of the original cosmic ray. These measurements have revealed that some cosmic rays possess energies far greater than those produced in human-made particle accelerators. The most energetic cosmic ray ever recorded carried an energy of about 300 billion electron volts. That value is so large that scientists gave the event a memorable nickname, the "Oh my God" particle. The name reflects the reaction researchers reportedly had when they first calculated its energy. Although cosmic rays themselves are individual particles, the energy they carry can be interpreted as a kind of temperature. In physics, temperature relates to the average kinetic energy of particles in a system. A single cosmic ray particle with enormous kinetic energy can be compared to particles in an extremely hot gas. If many particles had similar energies, the resulting system would correspond to temperatures far beyond those found in most astrophysical environments. In that sense, cosmic rays represent particles carrying fragments of the universe's most extreme energies across vast distances. Their journeys can last millions or even billions of years. Some cosmic rays may originate from distant galaxies, travelling through intergalactic space before eventually encountering Earth. During their travels, they interact occasionally with radiation fields and magnetic fields, gradually losing energy. Despite these losses, many still arrive with enormous energies intact. Studying cosmic rays helps scientists explore how the universe accelerates particles and distributes energy across space. Their interactions with Earth's atmosphere also provide a natural laboratory for particle physics. When cosmic rays strike atmospheric atoms, The resulting particle showers resemble miniature versions of the collisions studied in particle accelerators. Before large accelerators were built, many discoveries in particle physics came from studying cosmic rays. In fact, several fundamental particles, including the positron and the muon, were first detected through cosmic ray experiments. Even today, cosmic rays continue to provide valuable information about high-energy processes occurring far beyond our solar system. Although cosmic rays carry enormous energy, they do not represent a permanent hot environment like a star or accretion disk. Instead, they are moving packets of energy travelling through space. Their significance lies in the insight they provide into the universe's most energetic accelerators. Some of those accelerators involve collapsing stars, powerful magnetic fields, or the enormous gravitational engines at the centres of galaxies. After exploring the heat of stars, exploding supernovae, neutron stars, black hole accretion disks, and even the tiny fireballs created in particle accelerators, a natural question begins to appear. Can temperature keep increasing forever? Or is there some ultimate limit, a point beyond which heat cannot rise any further? It might feel intuitive to assume there is no limit. If temperature simply measures the energy of moving particles, then perhaps adding more and more energy should always raise the temperature. After all, a pot of water can be heated higher and higher if you continue adding heat. But when physicists began examining extreme conditions more carefully, they realized that the situation becomes more complicated at very high energies. At ordinary temperatures, increasing heat simply means particles move faster. Molecules vibrate more vigorously, atoms collide more energetically. If enough energy is added, solids melt into liquids and liquids boil into gases. Continue heating even further, and atoms themselves lose their electrons, forming plasma. So far, each step simply involves giving particles more energy. But eventually the energy becomes so large that the structure of matter begins to change in deeper ways. At temperatures of trillions of degrees, protons and neutrons themselves break apart into quarks and gluons, forming the quark-gluon plasma discussed earlier. Matter no longer resembles atoms or nuclei. Instead, it becomes a dense fluid of fundamental particles. Even then, the question remains, could temperatures continue climbing indefinitely if enough energy were added? To answer this, physicists look at how energy behaves when it becomes extremely concentrated. Temperature corresponds to the average kinetic energy of particles. But as energy increases, something interesting begins to happen. New particles can appear. According to Einstein's famous relationship between mass and energy can transform into matter. When enough energy exists in a small region, it can produce pairs of particles and antiparticles. In extremely energetic environments, energy no longer goes entirely into making particles move faster. Instead, part of that energy begins creating additional particles. The system becomes crowded with more and more matter. This process acts as a kind of pressure valve for extreme energy densities. Rather than allowing particle speeds to increase without bound, the energy spreads out by producing additional particles. As temperatures rise further, particle interactions become increasingly complex. New particle types appear, collide, and decay into other particles. The number of possible interactions grows rapidly. The system becomes a dense and chaotic environment, where energy constantly shifts between motion and particle creation. Physicists studying high-energy environments realize that there might be a theoretical limit beyond which temperature cannot be meaningfully defined, using the ordinary concepts of particle motion. The idea of a maximum temperature arises when gravity enters the picture. Under normal conditions, gravity is extremely weak compared with other forces acting on particles. But when energy densities become enormous, gravity begins to play a much larger role. Energy itself contributes to gravity. If enough energy is packed into a sufficiently small space, the gravitational effects become significant. In fact, if energy concentration becomes high enough, it could theoretically create a tiny black hole. This leads physicists to consider the scale where quantum mechanics, gravity, and particle physics all become equally important. That scale is defined by a set of natural units known as the Planck units, named after the physicist Max Planck. Planck units arise from combinations of fundamental constants, the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. These constants describe the basic behaviour of the universe. From them, physicists derive quantities such as the Planck length, Planck time, and Planck temperature. The Planck temperature represents an estimated upper limit to temperature. Its value is roughly 1.4 times 10 to the power of 32 Kelvin. That number is so large that it is difficult to comprehend. It is far hotter than the temperatures produced in particle accelerators, hotter than any supernova, and hotter even than the conditions believed to exist shortly after the Big Bang. At temperatures approaching this level, the known laws of physics begin to break down. Gravity becomes as strong as the other fundamental forces. Quantum fluctuations of space-time itself become significant. The smooth geometry of space and time described by general relativity may no longer apply. Instead, space-time may behave more like a fluctuating quantum structure. Physicists do not yet have a complete theory that describes this regime. General relativity describes gravity very well on large scales, such as stars and galaxies. Quantum mechanics describes particles and forces on very small scales. But combining these two frameworks into a single theory of quantum gravity remains one of the major challenges in modern physics. At temperatures near the Planck temperature, both effects become equally important. Without a complete theory of quantum gravity, scientists cannot fully describe what matter or energy would do under those conditions. One possibility is that our current concept of temperature would cease to be meaningful. Temperature relies on the idea of particles moving within space-time. But if space-time itself becomes unstable, or fluctuates at the quantum level, the entire framework used to define temperature may no longer apply. In other words, beyond this point, asking about temperature may not make sense in the usual way. The Planck temperature therefore represents not just a physical limit, but also a boundary in our understanding. It marks the point where current theories stop providing reliable predictions. Interestingly, the early universe may have briefly reached temperatures near this limit. Immediately after the Big Bang, when the universe was extremely dense and small, temperatures could have approached the Planck scale. As the universe expanded, it cooled rapidly, moving away from that extreme regime into the more familiar physics we observe today. Because the universe cooled so quickly, those earliest conditions lasted only a tiny fraction of a second. Today, no known natural process produces temperatures anywhere near the Planck temperature. Even the most energetic cosmic events fall far short of this theoretical boundary. Yet the concept of a maximum temperature still provides insight into the nature of the universe. It reminds us that the laws of physics may have deeper layers that remain hidden under normal conditions. Only in the most extreme environments do those deeper principles begin to reveal themselves. Physicists continue searching for clues about how the universe behaves at these extremes. Experiments with particle accelerators, observations of black holes, and studies of the cosmic microwave background all contribute pieces of the puzzle. Each discovery helps refine our understanding of energy, matter, and the fundamental forces governing the cosmos. For now, the Planck temperature remains a theoretical frontier rather than an observed reality. But thinking about such extremes provides a useful perspective. The heat of stars, supernovae, and even quark-gluon plasma might seem unimaginably intense. Yet compared with the Planck scale, those temperatures occupy only a small portion of the possible range allowed by physics. The universe began in a state far hotter than anything we observe today. There comes a point when exploring the extremes of heat where familiar comparisons stop being useful. Earlier we talked about temperatures in stars, then in supernova explosions, and then the trillions of degrees produced in particle accelerators. Each step seemed impossibly hotter than the one before it. Yet even those astonishing temperatures are still far below what physics suggests might be the ultimate limit. That theoretical boundary is the Planck temperature. The Planck temperature represents the point where our current understanding of physics begins to break down. It is not simply another very large number on the temperature scale. Instead, it marks the region where the fundamental rules describing matter, energy, gravity, and space itself can no longer be treated separately. To understand why this temperature matters, it helps to look at how physicists think about the basic structure of the universe. Modern physics relies on two enormously successful frameworks. One of them is quantum mechanics, which describes how particles behave on extremely small scales. The other is general relativity, Einstein's theory explaining how gravity shapes space and time on large scales. Both theories have been tested repeatedly and have proven incredibly accurate within their respective domains. Quantum mechanics explains the behaviour of atoms, electrons, and subatomic particles. It predicts how particles interact through forces such as electromagnetism and the strong nuclear force. General relativity explains how massive objects warp space-time and create gravity. It accurately describes the motion of planets, the bending of light near massive bodies, and the structure of black holes. But there is a problem. The two theories are not easily combined. In everyday conditions, this conflict does not cause trouble. Most physical situations involve either very small particles where gravity is negligible, or very large objects where quantum effects are insignificant. However, when energy densities become extremely high, both theories must operate at the same time. That happens at the Planck scale. The Planck scale is defined using three fundamental constants of nature: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. When these constants are combined mathematically, they produce a set of natural units that describe the smallest meaningful scales of space, time, and energy. Among these values are the Planck length, the Planck time, and the Planck temperature. The Planck temperature is roughly 1.4 times 10 to the power of 32 Kelvin. Writing it out reveals just how enormous that number is: 100 quintillion degrees. At temperatures approaching this level, the energy contained in individual particles becomes so large that gravity begins influencing particle interactions in a way that ordinary physics cannot describe. In simpler terms, particles become energetic enough that their gravitational effects are no longer negligible. At that point, space-time itself may begin to fluctuate. Normally we imagine space as a smooth stage where physical events take place, but quantum theory suggests that at extremely small scales, even empty space is not truly empty. Instead, it contains tiny fluctuations of energy that appear and disappear constantly. At Planck scale energies, these fluctuations could become so intense that space-time behaves more like a frothy, constantly shifting structure rather than a smooth background. Physicists sometimes describe this idea as quantum foam. In such conditions, the ordinary concepts used to measure distance and time might lose their meaning. The geometry of space-time could fluctuate so rapidly that it becomes impossible to define stable coordinates. And if space-time itself becomes unstable, then our usual definitions of motion and energy, both essential for defining temperature, may no longer apply. This is why the Planck temperature is often described as the ultimate edge of physics. Beyond this point, the equations used in modern science cannot reliably predict what happens. Some researchers believe that reaching this temperature would require concentrating enormous amounts of energy into an extremely small region. If enough energy were packed together, gravity might form microscopic black holes. These tiny black holes would appear and disappear extremely quickly, constantly forming and evaporating through quantum processes. Others suggest that at such extreme energies, the fundamental forces of nature may merge into a single unified interaction. Today, we recognize four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But theoretical models suggest that at very high energies, these forces may have once been unified. In the earliest moments after the Big Bang, the universe may have existed in such a unified state. As it expanded and cooled, the forces gradually separated into the distinct interactions we observe today. The Planck temperature may correspond to the energy scale where this unification originally occurred. Understanding that regime could reveal deeper principles governing the universe. Unfortunately, testing these ideas directly remains far beyond current technological capabilities. Even the most powerful particle accelerators ever built produce energies trillions of times lower than those associated with the Planck scale. Creating Planck temperature conditions in a laboratory would require machines vastly more powerful than anything humans have constructed. For now, scientists study this frontier through theoretical physics. Researchers develop mathematical models attempting to unify gravity with quantum mechanics. Several candidate theories exist, including string theory and loop quantum gravity. Each proposes different ways that space-time and particles might behave at Planck scale energies. Although these theories remain incomplete, they provide hints about how the universe may operate at its most extreme limits. One intriguing possibility is that the Planck temperature was reached only once in the history of the universe. During the earliest fraction of a second after the Big Bang, the universe was compressed into a tiny volume with enormous energy density. At that time, temperatures may have approached the Planck scale. If that is correct, then the laws of physics we observe today emerged as the universe cooled and expanded away from that extreme state. This idea suggests that the familiar structure of particles, forces, and space-time evolved from conditions that were once far more chaotic and energetic. The early universe might have passed through a series of transitions as it cooled. At first, the fundamental forces separated. Then quarks combined into protons and neutrons. Later, nuclei formed, followed eventually by atoms. Over billions of years, gravity gathered matter into stars and galaxies. All of that structure grew out of the cooling of a universe that began in a state of extraordinary heat. Thinking about the Planck temperature therefore connects two ideas. On one hand, it represents a theoretical upper limit of temperature. On the other hand, it marks the beginning of the thermal history of the cosmos. Everything we observe today exists because the universe cooled from that extreme starting point. At the beginning of the universe, heat was everywhere. Not just in one place, not concentrated inside a star or a galaxy, but spread through all of space. Every region of the cosmos existed in a state of intense energy. Particles collided constantly, radiation filled every direction, and the temperature was so high that the familiar structure of matter could not exist yet. Over time, however, something remarkable began to happen. The universe started to cool. This cooling did not occur because heat escaped into some external space. Instead, it happened because space itself was expanding. As the universe grew larger, the energy contained within it spread across a greater volume. When energy becomes more spread out, the average energy of particles decreases and temperature falls. In other words, the universe cooled because it grew. During the earliest moments after the Big Bang, temperatures were unimaginably high. Earlier we explored the idea that the universe may have reached temperatures close to the Planck scale, the theoretical limit where our current understanding of physics begins to break down. Those extreme conditions did not last long. The universe expanded extremely rapidly during its first moments. As expansion continued, temperatures dropped quickly, allowing new structures to form. Within the first tiny fraction of a second, the universe was filled with quarks, gluons, electrons, photons, and other fundamental particles. These particles moved through a dense plasma where collisions occurred constantly. As the universe cooled slightly, quarks began combining into protons and neutrons. That step represented a major change in the structure of matter. Instead of a fluid of free quarks, the universe now contained stable building blocks that could later form atomic nuclei. But the cooling process continued. During the first few minutes after the beginning, temperatures remained extremely high, billions of degrees. In that environment, protons and neutrons collided frequently enough to form the nuclei of light elements. This period is known as Big Bang nucleosynthesis. Hydrogen nuclei, consisting of single protons, formed in enormous quantities. Some protons and neutrons combined to form helium nuclei, containing 2 protons and 2 neutrons. Small traces of lithium and other light elements also appeared. These nuclei would later become the raw material for stars and galaxies. Even after this stage, the universe remained a hot plasma. Electrons were still moving freely, unable to remain bound to atomic nuclei because the surrounding radiation was too energetic. Photons scattered constantly from charged particles, filling space with an opaque glow. Light could not travel far without colliding with something. The universe during this period would have appeared like a bright fog. This phase lasted for hundreds of thousands of years. During that time, expansion gradually reduced the temperature further. Eventually, the temperature fell to around 3,000 degrees Celsius. At that point, electrons could finally combine with nuclei to form stable atoms. Hydrogen atoms formed throughout the universe, along with helium atoms created earlier during nucleosynthesis. This transition changed the universe dramatically. With electrons now bound inside atoms, photons could travel freely through space without constant scattering. The bright fog cleared, and light began moving across the cosmos uninterrupted. The radiation released at that moment still fills the universe today. As the universe continued expanding, the wavelengths of that radiation stretched and cooled. What once glowed with visible light now appears as faint microwave radiation, known as the cosmic microwave background. This radiation represents the oldest light we can observe. Measurements of the cosmic microwave background provide scientists with a snapshot of the universe, when it was only about 380,000 years old. Although the universe had cooled dramatically compared with its earliest moments, it was still hotter than most environments we encounter today. Yet cooling continued steadily. Over millions of years, the temperature of the universe dropped further as expansion carried galaxies farther apart. Meanwhile, gravity began shaping the distribution of matter. Small variations in density that existed in the early universe gradually grew larger. Regions containing slightly more matter attracted additional gas and dust through gravitational pull. These growing clouds eventually collapsed under their own gravity. Inside those collapsing clouds, temperatures began rising again locally. Although the overall universe was cooling, gravity could concentrate matter in specific regions. As gas clouds contracted, the pressure and temperature in their centres increased. This process eventually ignited the first stars. These early stars formed hundreds of millions of years after the Big Bang. They were likely very massive and extremely hot compared with many stars seen today. Their formation marked the end of the universe's earliest dark ages. Once the first stars ignited, they began producing light and heat through nuclear fusion. Their radiation illuminated surrounding gas and influenced the formation of future generations of stars. Despite the birth of these hot stellar furnaces, the overall universe continued cooling. The expansion of space remained the dominant trend shaping cosmic temperature. Galaxies formed and evolved, stars ignited and died, and new elements were created through stellar fusion and supernova explosions. Yet throughout all these processes, the background temperature of the universe steadily declined. Today, the cosmic microwave background has cooled to about 2.7 Kelvin above absolute zero. That means the average temperature of empty space is just a few degrees above the coldest temperature physically possible. Compared with the fiery beginning of the universe, the modern cosmos is remarkably cool. Stars, planets, and other structures exist as isolated pockets of warmth, surrounded by vast regions of cold space. The sun, for example, shines with surface temperatures of thousands of degrees, yet the space between planets remains extremely cold. If sunlight didn't warm Earth's surface, our planet would quickly freeze in the darkness of space. This contrast highlights an important feature of the universe. Heat tends to spread out over time. Regions of high temperature gradually release energy into their surroundings. As energy spreads more evenly, temperature differences decrease. This process is related to the concept of entropy. Entropy measures the degree of disorder or randomness in a system. In many physical processes, entropy tends to increase over time. Energy spreads out and systems move toward more uniform states. The cooling of the universe reflects this principle on the largest possible scale. In the beginning, energy was concentrated in an extremely dense and hot state. As the universe expanded, that energy dispersed across an ever-growing volume. The result has been a gradual decline in the average temperature of the cosmos. Yet the story is not simply one of constant cooling. Within galaxies, gravity continues gathering matter into stars and other structures. These regions create localized pockets of intense heat. Stars burn for millions or billions of years before exhausting their fuel. Some end their lives quietly, while others explode as supernovae, briefly creating temperatures far hotter than their stellar cores. These processes recycle matter and energy through galaxies. The heat produced by stars powers many of the phenomena we observe in the universe today. It drives stellar winds, lights up nebulae, and shapes the environments where planets can form. Without the heat of stars, the universe would be a far darker and colder place. Still, even these sources of heat represent temporary phases. Stars eventually run out of fuel. When they do, they fade into compact remnants such as white dwarfs, neutron stars, or black holes. Over extremely long timescales, the number of active stars in the universe may gradually decline. As that happens, the cosmos could become even colder. Astronomers sometimes refer to the distant future of the universe as a period of gradual thermal decline. If star formation slows and eventually stops, the universe may enter an era dominated by faint stellar remnants and dark, cold space. But that future lies trillions of years ahead. For now, the universe still contains countless stars shining across billions of galaxies. Each of those stars contributes warmth and light to its surroundings, even as the background temperature of the cosmos continues its slow descent. Looking across the vast span of cosmic history reveals an extraordinary transformation. The universe began as a state of unimaginable heat, where particles collided in a dense ocean of energy. Over billions of years, expansion cooled that fiery beginning into the calmer cosmos we see today. And within that cooler universe, pockets of heat continue to appear wherever gravity gathers matter and ignites new stars. Heat might seem like a simple idea at first. Most people experience it in very ordinary ways: a warm cup of tea in the morning, sunlight heating the surface of the ground, the feeling of stepping outside on a hot summer afternoon. Yet temperature is not just a small detail of daily life. It is one of the most important factors shaping the entire universe. From the birth of stars to the formation of planets, from the chemistry of life to the evolution of galaxies, temperature quietly governs what can exist and what cannot. Understanding heat is therefore not only about discovering the hottest place in the universe, it is also about understanding why the universe looks the way it does, and why certain regions become capable of supporting complex structures like planets and living organisms. At the most basic level, temperature describes the motion of particles. Atoms and molecules are never truly still. Even in solid materials, particles vibrate constantly around their positions. As temperature increases, these vibrations grow stronger. In liquids and gases, particles move more freely, colliding and bouncing past one another. When temperatures become extremely high, atoms lose electrons and become plasma. And at even higher energies, atomic nuclei themselves can break apart into their fundamental components. Because temperature controls particle motion, it also determines which forms of matter can exist. Take water as a familiar example. At low temperatures, water becomes ice, where molecules lock into a rigid structure. As temperature rises, the molecules gain enough energy to break free from that structure, forming liquid water. Increase the temperature further, and the molecules escape into the air as water vapour. These transitions between solid, liquid, and gas are controlled entirely by temperature and energy. In the universe, similar principles apply to much larger systems. Clouds of gas drifting through galaxies behave differently depending on their temperature. Cold gas clouds can collapse under gravity to form stars. Hot gas, on the other hand, tends to expand outward rather than collapsing. Temperature therefore plays a direct role in determining where stars can form. In regions where gas remains cool and dense, gravity slowly gathers material together. Over time, these clouds contract, and the central temperature begins to rise. If enough mass accumulates, the temperature in the core becomes high enough for nuclear fusion to ignite. A star is born. Once fusion begins, the star generates enormous amounts of heat and radiation. This energy pushes outward, balancing the inward pull of gravity and stabilizing the star for millions or billions of years. Without reaching the necessary temperatures, fusion could never begin. This means temperature determines whether a cloud of gas remains a cold nebula or transforms into a glowing star. Temperature also influences the types of stars that form. Massive stars compress their cores more strongly, reaching higher temperatures that allow faster nuclear reactions. These stars burn brightly and live relatively short lives. Smaller stars reach lower core temperatures and burn fuel more slowly, allowing them to shine steadily for billions or even trillions of years. The balance between gravity and heat defines the life cycle of stars. Temperature continues to shape events even after stars die. When massive stars collapse and explode as supernovae, the extreme heat created during the explosion allows new elements to form. Atoms heavier than iron are forged in these fiery events and then scattered across space. These elements later become part of future stars, planets, and eventually living organisms. In this way, temperature influences the chemical richness of the universe. Without those intense bursts of heat during supernova explosions, many of the elements essential for life would never exist. Carbon, oxygen, calcium, and iron all owe their presence to the nuclear reactions occurring inside stars and the explosive environments where those stars end their lives. Temperature also determines whether planets can form and remain stable. Planets begin as small grains of dust within rotating disks of gas surrounding young stars. These particles collide and stick together, gradually forming larger bodies. But if temperatures are too high near the star, volatile materials evaporate and cannot condense into solid particles. This is why rocky planets like Earth tend to form closer to stars, while gas giants often form farther away where temperatures are lower. The distribution of temperature within a planetary system shapes the types of worlds that appear. Once planets form, temperature continues playing a crucial role in determining their environments. Earth exists within a region around the Sun often called the habitable zone. In this region, temperatures allow liquid water to exist on the surface. Liquid water is essential for the chemistry of life as we know it. If Earth were significantly closer to the Sun, temperatures would rise high enough to evaporate oceans and create a runaway greenhouse effect similar to what happened on Venus. If Earth were much farther away, the planet might resemble Mars, where colder temperatures allow water to freeze or escape into space. This narrow range of temperatures highlights how sensitive planetary environments can be. Life depends not only on the presence of certain elements, but also on temperature conditions that allow complex chemistry to occur. Biological processes rely on molecules interacting with one another in precise ways. Proteins fold into specific shapes, chemical reactions occur at controlled speeds, and cellular structures remain stable only within certain temperature ranges. Too much heat disrupts these structures. Too little heat slows chemical reactions so much that biological processes cannot function effectively. This delicate balance explains why life on Earth thrives within a relatively narrow temperature range, compared with the extreme environments found elsewhere in the universe. Even so, life has proven remarkably adaptable. Some microorganisms survive in hot springs where temperatures exceed 90 degrees Celsius. Others inhabit deep ocean vents, where superheated water emerges from beneath the sea floor. In colder environments, certain organisms can survive in frozen conditions, where temperatures drop far below the freezing point of water. These examples demonstrate that life can tolerate a wider range of temperatures than once believed. Still, there are limits. Beyond certain extremes, the molecular machinery of life breaks down. Temperature also shapes planetary atmospheres. Warm temperatures allow gases to remain active and circulate through atmospheric systems. Heat drives winds, storms, and ocean currents, distributing energy across a planet's surface. On Earth, sunlight heating the equator creates temperature differences that drive atmospheric circulation. These circulation patterns influence climate, weather systems, and ocean currents. Without temperature differences, these dynamic systems would not exist. The importance of heat extends even beyond planets and stars. Galaxies themselves contain regions of hot gas that fill the space between stars. In clusters of galaxies, enormous clouds of plasma reach temperatures of tens of millions of degrees. These hot gases emit X-rays that astronomers use to map the distribution of matter within galaxy clusters. The temperature of this gas reveals how galaxies interact and evolve within their cosmic environments. Heat therefore acts as a tracer of energy across the universe. Wherever energy concentrates, temperature rises. Observing temperature differences allows scientists to identify the physical processes shaping stars, galaxies, and cosmic structures. Even the faint glow of the cosmic microwave background carries information about the early temperature of the universe. Tiny variations in that radiation reveal the initial conditions from which galaxies eventually formed. Temperature, in other words, leaves fingerprints throughout cosmic history. By measuring those thermal fingerprints, astronomers can reconstruct events that occurred billions of years ago. From the fiery birth of the universe to the gentle warmth of sunlight reaching Earth today, temperature has guided the evolution of the cosmos. Heat drives nuclear fusion in stars, powers atmospheric circulation on planets, and shapes the chemical reactions that allow life to exist. Without the right temperatures at the right times, the universe would look very different. Stars might never ignite, planets might never form, complex chemistry might never develop, and life, as far as we understand it, would never appear. So when we ask about the hottest places in the universe, we are really asking something deeper. We're exploring how temperature influences the structure and history of everything around us. From the blazing interiors of stars to the delicate warmth that allows life to flourish on a small blue planet, heat connects every scale of the cosmos. Somewhere out in the universe, at this very moment, a star is exploding. In another distant galaxy, gas is spiraling into a black hole, heating until it shines with intense X-rays. Far away from both of those places, a particle accelerated by an ancient supernova is racing through space at nearly the speed of a light, carrying enormous energy across millions of light years. The universe is filled with extraordinary heat. Throughout this journey, we have explored many of the places where temperature reaches astonishing levels. We looked at the warmth we experience on Earth, and then moved outward to the Sun, our nearby stellar furnace. From there, the scale expanded to include hotter stars, violent supernova explosions, neutron stars compressed into city-sized spheres, and the brilliant disks of gas swirling around black holes. Each step revealed environments where particles move faster, collisions become more energetic, and matter enters increasingly extreme states. Then the story stretched even further. We explored quasars capable of shining brighter than entire galaxies. We examined the first moments after the universe began expanding, when everything existed in a state of intense heat. We saw how scientists recreate tiny fragments of those early conditions inside particle accelerators, producing temperatures of trillions of degrees for brief instants. And beyond even those extremes, physics suggests theoretical limits like the Planck temperature, where the very structure of space-time may begin to fluctuate and our current theories lose their certainty. All of these environments reveal something important. Heat is not just a property of a place, it is a measure of energy and motion. Wherever energy becomes concentrated, temperature rises. Wherever energy spreads out, temperature falls. The entire history of the universe can be understood through that simple idea. In the beginning, energy was compressed into a dense and incredibly hot state. As space expanded, that energy spread outward, cooling the cosmos over billions of years. Stars formed from collapsing clouds of gas, igniting new pockets of intense heat. Galaxies assembled, planets appeared, and eventually life emerged on at least one small world. Yet through all of these events, the overall trend has remained the same. The universe is cooling, not quickly on human timescales, but steadily across cosmic history. The fiery beginning has gradually given way to a calmer and colder cosmos. The background temperature of space today is only about 2.7 degrees above absolute zero. Most of the universe is filled with darkness and cold, interrupted here and there by the glowing warmth of stars. Those stars will not shine forever. Over extremely long periods of time, even the most massive stars exhaust their nuclear fuel. When they do, they collapse into remnants like white dwarfs, neutron stars, or black holes. Eventually, star formation itself may slow as galaxies use up the gas needed to create new stars. If the universe continues expanding for trillions of years, it may become a place where bright stellar fires grow rarer. The distant future could be dominated by faint stellar remnants and vast stretches of cold, dark space. But that future lies unimaginably far ahead. Right now, the universe still contains enormous energy. Billions of galaxies shine with countless stars. New stars continue forming inside glowing nebulae. Supernova explosions scatter heavy elements across space, creating the raw material for future planets. The cosmos remains an active and evolving place, and on a small planet orbiting an ordinary star, life has developed the ability to observe and understand that universe. From our vantage point on Earth, we can measure the temperatures of distant stars, detect X-rays from black holes, and recreate fragments of the early universe in underground laboratories. Using telescopes and detectors, we read the faint thermal signals left behind by cosmic events billions of years ago.